Hello and welcome to another episode of Microbially Speaking. I'm your host, Kevin Stinson. If this is your first time joining us, welcome. And if you're a returning listener, then welcome back. For today's episode, we are still talking Ebola, everyone's favorite nightmare of a virus. And as of June 9th, the CDC summary report on our current Bundibugyo outbreak in the DRC and Uganda shows us at 635 confirmed cases with 137 deaths in the DRC and another 19 cases and 2 deaths in Uganda. Now, these most recent numbers do officially mark this as the third largest Ebola outbreak in history. Definitely the largest Bundibugyo virus outbreak on record. And this one's only really beat out by two large Zaire or Ebola Zaire outbreaks in the past. The first one, the big one, is known as the Western Africa Ebola epidemic. It was a huge outbreak in Sierra Leone, Liberia, and Guinea between December 2013 and June 2016. In that outbreak, we saw over 28,000 cases and 11,000 deaths from Ebola Zaire. The second big outbreak, the second largest in history, also again caused by Ebola Zaire, was known as the Kivu Ebola epidemic, hitting the DRC and Uganda right where we see our current outbreak today, with 3,400 cases and 2,200 deaths between August of 2018 and June of 2020. Now, there's a few telling points when we look at these figures that really help us conceptualize what's happening with our current Bundibugyo outbreak. First off, look at those case fatality rates. They are significantly higher in those two large outbreaks compared to what we're seeing today. And we've talked about that in previous episodes. We've talked about that in the inaugural episode on Ebola 2 weeks ago. The Zaire virus that was causing the West African Ebola epidemic, as well as the Kivu Ebola epidemic, those were both, that virus has a significantly higher severity and case fatality rate than what we see with the Bundibugyo virus. Now, the lower case fatality is certainly a good thing from a patient outcome. But we've talked about this before. It does pose challenges with trying to identify cases because you have a lot of cases who are going to be far more asymptomatic or at least minimally symptomatic, but may still be infectious. And so that becomes really difficult to implement effective identification of infectious cases and identification of contacts when you have someone who's minimally ill and isn't really showing all of the severe hemorrhagic presentations of Ebola like you see with the more severe Ebola Zaire. But there's perhaps a bigger takeaway from these two large epidemics because both of them have a unique attribute on them, which is how long they spanned. Both of them spanned multiple years, whereas most Ebola outbreaks with much smaller cohorts have only been a couple of months long. Now, we talked about this last time. There's a real concern with this outbreak that with sufficiently large enough case count and the challenges with implementing all of our public health and infection prevention control measures in this region, this could be a problem that just continues to smolder for a long period of time. Continue to smolder for months or even years before it can officially be called over. And that means what we can expect to see, or what we may see, is that the disease will flare up over time with large amounts of transmission in small communities throughout the DRC and Uganda and neighboring areas. But it also means that there's a risk that we will see cases seeded from this outbreak into other countries, both neighboring African countries and countries further abroad. But what's the risk of that happening? What would the risk be of Ebola making its way here to North America? Well, let's look back again at that largest Ebola outbreak on record, the West African Ebola outbreak, where we had 28,000 cases. It took 28,000 cases to see any widespread transmission beyond 1 or 2 countries. So while that one was primarily localized as an epidemic in Sierra Leone, Liberia, and Guinea, we did see cases and limited local transmission in Nigeria and Mali, two countries outside of the immediate outbreak area, but albeit with only 20 and 8 cases in those two countries respectively. What we did also see, and this is unique to this outbreak, is virus seeded into 3 European countries, as well as the United States, actually. Italy, Spain, and the UK each had a single case where an aid worker went to Sierra Leone or went to the impacted areas, was returned home, and subsequently developed an infection, subsequently developed an Ebola Zaire infection. Now, in all 3 of those cases, these individuals were in quarantine upon return. They were rapidly identified as ill, rapidly identified as positive, kept in very strict isolation, and there was no risk of further transmission outside of the individual. But the US had a slightly different experience. So the US had a Liberian citizen visiting family in Dallas when he developed symptoms. He initially developed symptoms of abdominal pains and a fever. And he presented to the hospital, and the USAMRIID discharged him with a prescription for antibiotics. The emergency department failed to capture that he was a traveler recently arriving to the United States from Liberia. Now, he went home and continued to worsen. And a few days later, he returned to hospital with significantly worsening symptoms, including vomiting, diarrhea, and hemorrhagic symptoms. This time, his travel history was really quickly flagged. He was quickly isolated and eventually tested positive for Ebola Zaire. Now, this case became the first reported case of Ebola Zaire or Ebola virus disease in North America. And the US also saw the first ever instance of local transmission attributed to this case. 2 healthcare workers who were involved with his care subsequently both developed symptoms and tested positive for Ebola Zaire virus. Now, obviously, this was huge news at the time, but as expected, once the proper risk was identified and once isolation, infection prevention control, those quarantine measures were put into place, it was really effective at rapidly controlling further transmission. Now, the index case did pass away in this scenario, but both of the nurses who became infected survived. And to date, this remains the only example of an Ebola virus transmission in North America. But it was not the United States' first encounter with Ebola. So for that story, we're going to take a look a little bit further into the past. The year is 1989. And the place is Reston, Virginia. Reston is a town only a short 30-minute drive from the capital of Washington, D.C. And back in 1989, in a small, nondescript business park not far from Dallas Airport, there sat a small, squat little one-story research building owned by Hazelton Research Products. Now, this building was known as the Reston Primate Quarantine Unit. Hazelton Products was a company that bred, sold, and imported animals for scientific research, and part of that work included sourcing and importing non-human primates. At the time in 1989, the US imported close to 24,000 non-human primates into the country every year, either for scientific research, vaccine production, or just things like going to a zoo and going on some form of a display. But the country had regulations where importers were required to hold animals for a 31-day quarantine facility or quarantine period at designated federal facilities. Now, this quarantine period was based on the risk that these animals might be importing pathogens that are capable of infecting humans. So 31 days gave importers time to examine and monitor the animals, look for signs of infectious disease, and conduct tests for some diseases like tuberculosis. And that all had to be done prior to these animals moving anywhere else throughout the country and potentially causing any exposures. Now, this work was brought into effect in 1975, and not without good reason. A few years prior to that, in 1967, 30 people developed a severe viral infection in West German towns of Marburg and Frankfurt. And eventually 2 additional cases were found in the Yugoslavian town of Belgrade. Now, cases began much as a lot of these viral illnesses do, with generalized symptoms, fever, but they rapidly progressed. And in more severe cases, they manifested with hemorrhagic symptoms, hemorrhagic shock, and multi-system organ failure. 7 of the patients died. Now, the source of this outbreak was identified as African green monkeys, all sourced and imported in the same shipment, but going to multiple places. Scientists started investigating where was this outbreak coming from, or rather what was causing this outbreak, and they utilized electron microscopy to visualize what might be causing the disease. And in the cellular debris from infected people and animals, they found something unusual. They found amidst all of the dying and dead cells, the cellular debris, a filamentous-like organism that they initially thought was actually a bacteria. It resembled the spiral-shaped spirochete bacterias, or spirochete family of bacterias, more so than it did any known virus at the time. The virus was named Marburg in recognition of where it was initially identified and isolated. Now, Marburg is a very similar virus to Ebola, at least in the sense that they share a very similar structure, very similar life cycle, very similar biology, and very similar mechanism of causing disease. But when we recall back to what we talked about Ebola a few weeks ago, remember that when we said Ebola viruses is not actually one virus, but is a genus called the ortho-Ebola viruses with 6 distinct species in it. Marburg is one step further removed from that. Marburg exists in the same family as the ortho-Ebola viruses, but is a different genus. They're both members of the family Filoviridae, or the more common name for that is filoviruses. Marburg was humanity's first look at these filoviruses, and it would be close to a decade later before the now much better known Ebola viruses would ever be discovered. So by 1989, we'd now known about Marburg, we'd seen this outbreak, we've discovered now Ebola viruses, we've had outbreaks of Ebola viruses in Africa. The risk posed by importing non-human primates into the country and the possibility of bringing these filoviruses with them was very well established. And so we get our 31-day quarantine period in the United States. In October of 1989, Hazelton accepted a shipment of 100 crab-eating macaques from the Philippines and brought them to the Reston quarantine facility. Within a few weeks, the principal veterinarian for Hazelton, Dr. Dan Dalgard, started to note the death of monkeys. He found that 27 of that original batch of 100 had died. Now, it wasn't unusual for monkeys to die during the quarantine phase, but the typical death rate was usually somewhere around 10 to 15%, and so these animals were dying at a rate far greater than what was anticipated. Dalgard started to perform necropsies. He started to try to find what was killing his monkeys. And he found that the most likely cause of death was either dysentery or pneumonia, both of which were highly prominent causes of death in crab-eating macaques. The facility kept receiving more and more monkeys shipped from the same area of the Philippines, and by early November there were around 500 animals in the facility. But animals continued to become sick, and animals continued to die at a rate far greater than what should have been anticipated. Dalgard started to suspect a different cause. He started to suspect a virus called simian hemorrhagic fever virus, or SHF. Now, this is a virus that is highly lethal in monkeys, but doesn't cause disease in humans. As he kept seeing animals become sick and kept seeing animals die, he enlisted the help of Peter Jarling, a virologist working at the United States Army Medical Research Institute on Infectious Diseases, or USAMRIID, who had a lot of experience working with SHF. Jarling took tissue samples from 10 of these dead monkeys, and he sought to grow up the virus in cell culture. In essence, what you do is you take a small chunk of tissue and you add it to a flask with mammalian cells. The virus will enter into those cells, start replicating, and eventually will have enough virus there that scientists can then perform further tests and confirm what virus is in the samples. He was able to find that SHF was present in 3 of the 10 samples, so he gave off a presumptive diagnosis of SHF. At that point, Dalgard made the decision to euthanize the rest of the animals in the first shipment. At this point, they were already sick, SHF was in the room, there would be no real hope of salvaging that shipment. He also started to euthanize any sick animals in the second shipment in the hope of halting any further transmission. He performed necropsies and he documented his findings. Now, not long after this, an electron microscopist and a microbiology PhD candidate named Thomas Giesbert was working alongside one of Jarling's research technicians when they noticed that one of the cell culture samples just looked off. Now, cells kind of grow as a film on the bottom of a flask. And when they die, they detach and lift off and they start floating away. And similar to how a microbiologist gets familiar with grabbing a plate of bacteria, looking at that plate, and knowing by the appearance of the colonies what bacteria that may be, virologists become very adept at knowing how should a virus look when it's growing in cell culture. Or perhaps more importantly, how shouldn't it look when it's growing in cell culture? They brought this unusual specimen to Jarling, and the initial thoughts were that the cell culture had somehow become contaminated, but with bacteria. Jarling and Giesbert both took turns smelling the flask. They would uncork it and waft the odors towards them to see if they can smell anything distinctive, but they couldn't really find anything. Now, as a quick aside, it used to be very common practice to sniff things in a microbiology lab, particularly a bacteriology lab, to try to identify what was there. A lot of bacteria can be readily differentiated by their odors. It just probably isn't the safest option, especially when you're dealing with an unknown sample. So it's kind of fallen out of favor and is frowned upon as really not an intelligent way of identifying bacteria. That said, I do still occasionally fall back upon this habit when I'm in the lab because old habits do die hard. So Giesbert took the specimens and figured looking at them under an electron microscope would help understand what was going on. So unlike a usual microscope, when we think a typical microscope in a microbiology lab that looks at bacteria around 100 times, 400 times, or 1,000 times magnification, using light, electron microscope use beams of electrons to look at specimens at far greater magnification, up to 1,000,000 times magnification. But most viruses are examined around 500,000 times. The process to get them is also a lot more involved. It's not just a matter of take a little bit of liquid, put it onto a slide, put a cover on it, throw it under a microscope, and you can see it. The samples have to be prepared very specially. And so first step is to concentrate the specimen. You take a little bit of the liquid and you centrifuge it, usually in an ultra centrifuge capable of generating G-forces up to 1,000,000 times the force of gravity, because that's what you need to pull these extremely fine particles like viruses out of the fluid and create a small pellet. Now that pellet of viruses is what we're going to look at under the electron microscope. We embed that into a resin and we slice it into sections. The sections are less than 100 microns thick. We then take those sections and we affix them to something we call a specimen grid, and that's what's put under the microscope. Now, Giesbert did all of the prep work for these specimens and promptly left for an extended vacation because it was American Thanksgiving. So after his long weekend, he came back from Thanksgiving in 1989. He picked up his prepared specimens from the Reston monkey house and he fired up his electron microscope. And he was met immediately with a view of cellular debris, cells dying, and what he described as wall-to-wall filamentous viral particles. It was a filovirus, much like Marburg or Ebola. Now, filoviruses are universally classified as biosafety level 4 pathogens, BSL4, meaning they are managed under the most rigorous of laboratory precautions. Typically, when you're working with these in a BSL4 lab, you're wearing a pressurized spacesuit. Everything in the lab is under negative pressure. You walk in wrapped head to toe in this pressurized suit. You hook up to an air supply, it blows up the suit, and you are protected from the environment of that lab. Jarling had conducted all of this work in a BSL-3 lab. Far less protection available for any of the scientists working with these specimens. And in this lab, they'd handled the tissues. They'd amplified the virus. They'd tested the virus. Jarling and Giesbert even sniffed the flask chock full of this virus. Meanwhile, just a short drive away, Dalgard had been euthanizing and performing necropsies on animals for weeks. So to confirm this, they wanted to figure out what exactly was this virus. And so they went back to those samples from the 10 monkeys and they tested them against known filoviruses. 5 of those animals tested positive for Ebola. One of the deadliest viruses on the planet had been found 30 minutes from the capital of the United States. USAMRIID and CDC immediately launched into a joint response of the incident. And virologists Colonel C.J. Peters and veterinarians Colonel Jerry Jacks and Lieutenant Colonel Nancy Jacks, all from USAMRIID, started to lead a lot of that initial response. The ensuing days were a frenzy of activity. They wanted to confirm the diagnosis of Ebola as quickly as possible, so they went and grabbed more samples or more specimens of monkeys to start to perform necropsies in USAMRIID to confirm what may have been causing this disease. They also want to put immediate quarantine and infection prevention strategies into effect. All activity other than extreme essential animal husbandry activity in the monkey house was suspended, and a whole slew of additional PPE was required: Tyvek suits, respirators, double gloving, before anyone could go into one of the monkey rooms. At USAMRIID, Jerry and Nancy Jacks started to assemble a team of military and civilian volunteers who would deploy to Reston. Their mission was going to be very simple: euthanize every animal in the facility and decontaminate the building. In early December, the team arrived at the Reston quarantine facility, donned their PPE. They wore lightweight portable Raycal positive pressure suits. These are very similar to the suits that would be worn in a BSL-4 lab, but they don't require an external air supply. Instead, they have an internal blower unit. And they're what USAMRIID scientists had previously used going to Ebola outbreaks in Africa to investigate those early outbreaks and trying to figure out that virus. This lets the team work in that relative protected environment in a very hostile and infectious area. Over 3 days in early December, the team worked to euthanize 450 monkeys. They would sedate an animal first with ketamine on a syringe, or ketamine syringes mounted on a long pole where they can reach into the cage, pin the monkey up, and sedate them, pull them out, euthanize them, and then perform necropsies. Thousands of specimens of blood and tissue were collected. The bodies were all double or triple bagged, loaded into drums, and eventually sent off for incineration, with every single step wiping everything down with bleach to decontaminate. Once all the animals were euthanized, the decon team could move in. Their job was not easy. Every single surface in this facility had to be disinfected. Throughout the facility was blood, urine, and feces coating the floor, the walls, the cages, the ceiling. Even blood from all of these animals being necropsied was pouring down floor drains, and it was all potentially highly infectious with Ebola. So it all had to be meticulously cleaned and disinfected. The team scrubbed every single surface with bleach. Every single nook and cranny was furiously scrubbed with bleach. And when they were done, they sealed the whole facility so it was airtight, and they flooded it for 3 days with formaldehyde gas, looking to penetrate into any crack or any crevice that might have been missed, in the hopes of eradicating all evidence of the virus. So what happened, though, to all of the people exposed? Well, neither Jarling nor Giesbert, who handled these tissues in a BSL-3 lab, who sniffed these specimens full of the virus, ever developed symptoms. And neither did Dalgard, who euthanized all of these cases without appropriate PPE before the diagnosis of Ebola was made. None of the people in the labs ever developed illness when they handled the tissues. But one of Dalgard's animal handlers did develop antibodies to Ebola, suggesting they were likely infected. So what exactly happened here? Why didn't this become a massive outbreak amongst the populace? Well, let's recall back to our episode on Ebola 2 weeks ago. There are 6 known Ebola viruses. 3 of them are known to cause disease in humans. The species that hit the quarantine facility in Reston, thankfully, and what's subsequently been known as the Reston Ebola virus, is not one that causes disease in humans. Now, the reason behind this is not entirely known. We speculated a little bit or shared some of the speculation on this a few weeks ago. It's probably due, at least in part, to the inability to evade the human immune response, like we see in pathogenic Ebola species. And so what that means is that when the virus enters a human, it's a lot more readily identified and detected by the immune response and can be cleared out before it causes disease. But the story brings to light and brings to the imagination how this could have played out differently. If this had been Marburg or Ebola Zaire or any of those other pathogenic filoviruses that hit that facility, this could have been a far more significant outbreak. We see today the continued importation and use of non-human primates in research and for other purposes, and the US continues to enforce their mandatory quarantine period. Hopefully, stories like Reston serve as a cautionary tale on the importance of close adherence to those protocols and just how close the United States came to a far more severe outcome. Now, important to note, I'm far from the first person to share this story, and it's probably the most famous, or the story's been made most famous by Richard Preston's book, The Hot Zone. I remember reading this book early in my microbiology education and loved it. It made me want to be a microbiologist doing this kind of work. And I do admit that rereading it now, there's a lot of embellishment. There's a lot of creative liberties taken, especially looking at some of the strict microbiology and how the virus interacts with the host. But it is probably one of the best accounts of the sequence of events surrounding this outbreak. The book was the inspiration for the 1995 movie Outbreak, which of course is not at all based in reality, but I always thought it'd be amazing for the true story of Reston to be a movie or a miniseries. And lo and behold, I just discovered that in 2019 there is such a miniseries. Apple TV has a miniseries called The Hot Zone that did just that back in 2019, and I somehow have completely missed it. Now, I've abridged this story quite a bit for the sake of time for this podcast, so certainly if you want the whole story, I would definitely check out the book. I haven't actually watched the miniseries. It's like $20 on Apple TV. I'll probably get around to it sooner or later. But the book is definitely a fantastic telling of this story and was a major reference for this episode. I strive to fact check as much as possible using as many real resources like governmental resources or primary literature as I can, and referencing any statistics back to the CDC. But certainly a lot of this story is referenced directly out of Preston's book, The Hot Zone. And so with that, we'll come to an end on this week's episode of Microbially Speaking. Thanks so much for joining us today. If you enjoyed the episode, be sure to hit the like button. I think we'll put Ebola down for now. I think we're going to turn our next episode back to another topic, maybe get back to some bacterial topics. So be sure to subscribe to the channel so you don't miss out on future episodes. As always, if you have any thoughts, any comments that you from today's episode, throw them in the comments below. If you have a topic you'd like to explore in future episodes, certainly let me know. Otherwise, thanks again, and we'll see you next time on Microbially Speaking. Bye now.